nanoHUB-U, online instruction.
Welcome back to Unit 2 of our course, and this is the 6th lecture. Now, what we have done in the last few lectures is set up this basic framework, the NEGF equations. Now, in order to use these equations, the input you need is the sigma and the sigma in. Okay? And question is, how do you find them? And as I had mentioned earlier, these things come from the boundary conditions. So in a specific problem, the way you think is you have E psi equals H psi that applies to everything, but then the surroundings fix a certain boundary condition, and that is what is reflected in these sigmas. And so far we haven't really talked about that. We've tried to say, well, you have this sigma, so what kind of inflow does it cause? What kind of outflow does it imply? And so on. Now, what we'll be doing in this lecture is we'll take a 1D example and use the boundary conditions to actually obtain expressions for these sigmas. And for 1D examples, this is actually quite adequate. And what we'll do in the next unit, Unit 3, is we'll look at more complicated examples, two-dimensional examples, where you need different methods for finding these sigmas. But what we'll do in this lecture is do this general method that applies to one-dimensional examples. So the way we do it is, think of a 1D wire with these points starting from 0, 1, 2, 3, etc. And as we discussed in Unit 1, it can be described by a H matrix, which has these epsilons down the diagonal and the T's on the upper and lower diagonals. And what we showed in Unit 1 is that if you assume periodic boundary conditions, assume this thing is in the form of a ring, then you can obtain this dispersion relation. Now, what we want to do here is apply a different kind of boundary condition, what you might call an open boundary condition. That is, it's not a ring anymore. Ring is kind of a closed thing. Here it's not closed, it's open. So any wave electron that comes here kind of flows away and never comes back. And that is the boundary condition we want to use. And using that boundary condition, we'll obtain expression for the sigmas. So how do you do that? So basic approach then is what you might have seen if you have taken a course on quantum mechanics, or actually any wave theory type of course. That you have a device, you have an incident wave from one side, and we assume that electrons are incident only from the left and not from the right. So you have an incident wave which has an amplitude of B. And the reason I'm using B is we have already used A for this density of states. So just to avoid confusion, I'm using B here. And later on we'll talk about how we get the B. But this is just the amplitude of the incident wave. What's reflected is B times rho times that. This is the reflection coefficient. What's transmitted is B times tau. That's the transmission coefficient. And you'll notice I use the e to the power plus ik z, and I guess this is a discrete lattice, so the z becomes an integer small n times a, which is the lattice constant. And the way this wave is going backwards, which is why there's a minus ik, and that one has a plus ik. Okay. Now, next step is, if we go to the end of this thing on this side, so this is the nth point, this is the n plus 1 point. And what we want to do is write the wave function on the n plus 1 point in terms of what it is in the nth point. Because finally we want to have a device that only goes from 0 to n. We want to eliminate anything from outside. And so we want to write this in terms of that, and you'll see how we go about it. So first point is that if the transmitted wave looks like this, then psi n is equal to b tau times e to the power I k n a, whereas psi n plus 1 is the same with n plus 1 in place of n. And if I divide one by the other, I get that the ratio is e to the power plus I k. So that's the central result we are trying to get. psi n plus 1 equals e to the power I k a times psi n. Now on the left hand side, it's a little more complicated because we have both an incident wave and a reflected wave. Here there was only one wave. So on this side when we write it, it's like, let's try to write psi 0. So at point 0, n is equal to 0. So you have b from here and b rho from here. So psi 0 is b plus b rho. That's the incident wave, that's the reflected wave. The total wave function at 0 is that. Now if you look at the wave function at point 1, or minus 1 rather, this is minus 1. So the incident wave, I have to put a n equals minus 1. So I get b e to the power minus I k a. Here when I put n equals minus 1, I get b rho e to the power plus I k a. So those are the two equations, and what I want to do is, again, express psi minus 1, which is outside my domain, in terms of psi 0, which is inside my domain. And the way you do it is, you want to eliminate the rho and express this in terms of that. Now to do that, what you can do is, I can take the psi 0, multiply by e to the power I k a. So this becomes b e to the power I k a plus b rho e to the power I k a. Now you see I got the same thing here and here. So if I subtract one from the other, that will cancel out. So when I subtract, I get the psi minus 1 is equal to psi 0 e to the power I k a plus this thing, which is the difference between this one and that one. So just from subtracting, you'd get that equation. And that gets us this other result we are looking for, namely psi minus 1 is equal to psi 0 e to the power I k a minus this 2ib sine k a. So note the difference. On the right hand side, you just got psi n plus 1 is e to the power I k a psi n. Here also you have exactly the same factor, psi minus 1 is psi 0 times that, but there is also an additional term here. Okay, now how do you use that? Okay, this is where we go back to our original tight binding equations, the ones we had in unit 1. So for example, on the right hand side, we had an equation looking like this. E psi n is equal to t psi n minus 1 epsilon psi n plus t psi n plus 1. And what we want to do is get rid of that psi n plus 1 because n plus 1 is kind of outside our domain. We want to keep only from 0 to n. Well, we can use this expression to get rid of it. So instead of psi n plus 1, we can put e to the power I k a psi n, and that way that can be combined with this term to give you epsilon plus t e to the power I k a psi n. So now we have an equation that does not involve n plus 1 anymore. Similarly, on the left hand side, we want to get rid of the psi minus 1. So instead of psi minus 1, we put this in. And when we put that in, you again pick up this epsilon plus t e to the power I k a like before. But you also get an additional term due to this. So you get minus 2ibt sine k a. Now you see if you look at this, you have E psi n equals this at the right end, E psi 0 equals this at the left end. So going back to the original problem, let's say we got 3 points in our device, 0, 1 and 2. Then you see the H would look like a 3 by 3 matrix, epsilon down the diagonal, T is here. Now what we have picked up, because we eliminated psi n plus 1 using this boundary condition, we have picked up that extra term which multiplies psi n. And that is that extra term is the sigma 2. So it is like on the nth point, you are adding a t to the power I k a. Similarly, on the left hand side, you have a t to the power I k a on the 0th point. It's like having you have added that in there. So now if you add h plus sigma 1 plus sigma 2, it will look like the equations we have up there. Because at the 0th point, the epsilon will get added to that, just like this. At the nth point, this will get added to that, and just like that. So effectively, you see how the boundary conditions got translated into the sigma 1 and sigma 2. And these are also matrices, 3 by 3, just like H. Big difference though, H is a Hermitian matrix. This isn't, because a Hermitian matrix means it's equal to its conjugate transpose. What that means is elements on the diagonal must be real. Here, that's an element on the diagonal and it's complex. Now, the other thing we pick up on the left-hand side is a source term, like we had mentioned. That because there was this incident wave from here, that's what is reflected in as a S term is minus 2 IBT sine Ka. And that's only present at point 0 because the electron was incident from the left. And overall then, the new equations, you see, where it only goes from 0 to n, it only involves our domain. Everything outside has now been eliminated. The new equation now is E psi equals H psi plus sigma 1 plus sigma 2 psi plus S. See, if you take that equation and write it out, you'll get, exactly our same equations as before, except that the last equation on the left will look like this, last equation on the right will look like that. Now, next what we want to do is you have a sigma 1 and sigma 2. Let's get the gammas. How do you get the gammas? It's I times sigma 1 minus sigma 1 dagger. What's sigma 1 dagger? It's this conjugate transpose. Since it's a diagonal matrix, transpose doesn't matter, it's the conjugate. So when you take t to the power ik and ka, subtract its complex conjugate from it, you get minus 2t sine ka. You have to multiply by I also, so you get minus 2t sine Ka. Similarly, sigma 1 will give you minus 2t sine Ka here. So those are the gamma 1 and the gamma 2. Now one thing you'll notice, this minus 2t sine Ka appears at various places. And this quantity actually can be related to the velocity of the electron in the wire. Because you see, this wire, if it was a uniform wire, would have a dispersion relation looking like this. E equals epsilon plus 2t cosine Ka. That is, if you look outside here, where it's a uniform wire, the two ends are assumed to be uniform, then over there you'd have this Ek relation. And the velocity is de dk, which gives you that. So minus 2t sine Ka is like velocity h bar v over a. So you could use that to replace these quantities. Okay. So in which case you'll get a h bar v over a at these places. Now before I do that, I wanted to mention one little thing, and that is v is actually positive. There's a minus sign there, but the point is that t is negative. Because you see, usually if you remember, when you plot epsilon plus 2t cosine Ka, t is negative, which is why the minimum is at k equals 0. If t was positive, the maximum would have been at k equals 0. Right? But t is usually negative, so that's negative, and so this is positive. Now you might say, well, but then there may be some devices where the t is negative, where it actually looks like this. Where t is positive, so it actually looks like this. Sure, but in that case, the point to note is that when you have an outgoing wave at this contact, you see outgoing waves usually means plus k. That's what we have done here. But if it looks like this, an outgoing wave is actually a minus k. Why? Because whether a wave is outgoing or ingoing depends on this group velocity, which is dE dk. So here, dE dk is positive on this side, negative on this side. Here it's positive on this side and negative on that. So if you indeed had a Ek relation looking like this, then you should really be using that. Bottom line is, if t is negative, k is positive and this is positive, because gamma must always be positive. Gamma kind of represents the rate at which electrons leak out. And if it is negative, then instead of leaking out, it would be coming in, and that wouldn't be right. So this will always be positive. And if you happen to have a t that is positive, you should be using a k that is negative. Anyway, moving on then, we write all these gammas in terms of the velocity, h bar v over a, like before. and we have the S term, which is minus IB H bar V over A. If you want the sigma in, if you remember, what we need is sigma, from which you can get the gamma, and then you also need this sigma in, which is S1 times S1 dagger. And S1 dagger is, of course, this thing, conjugate transpose. And if you take the product, you'll get this sigma in over 2 pi. It will be this. Now, one fundamental relation that you can use whenever you're dealing with a contact in equilibrium is that sigma in must be related to gamma by this Fermi function of that contact. This is something we talked about earlier in this unit, and it comes from this requirement that if the wire were only connected to this contact, it should be in equilibrium and have the same occupation as the Fermi function of that contact. Now, just from this requirement, you can see what the value of B must be, because this is gamma, that's sigma in, multiplied by 2 pi. And in order to satisfy this relation, what you'll find is B square. I've assumed the B to be real, by the way. In general, it could have been complex, but for this purpose, I just assumed it's a real number. So B square is F1 times that. This is what is needed in order to make sure that this relationship is satisfied. On the other hand, this relation, if you think about it, also makes sense on its own, without invoking this requirement from statistical mechanics. Here, because the way you can think is what's B? Well, it's this amplitude of this wave function. So B squared is like the electron density. And what should be the electron density in that wire? Well, it should be the density of states. This is the density of states of just the waves traveling in the plus k direction into the device. That's A over 2 pi H bar V. I guess this is something we discussed in part A of the course, that in a uniform 1D wire, this would be the density of states. And density of states multiplied by F, that should be the electron density. So you could get this expression independently from that. On the other hand, just by invoking this rule, you could get the right value for B. Okay then, so I guess this is what I wanted to do in this lecture, namely give you a clear 1D example of how you get these two basic inputs. You see, we have the NEGF equations. To attack any problem, what we need is a sigma, whose anti-Hermitian part gives us the outflow, and the sigma in, which gives us the inflow. How do you get them? Well, it comes from the boundary condition and depends on the problem at hand. And what we did here is did a 1D problem and showed how that works. Okay? Next lecture then, we'll talk about this important concept of transmission and how you relate it to our NEGF method. Thank you.